Okay, so a few things I'd like to do today. The first thing is I'd like for you to take out your nuclear review homework. I want your homework last night was to do numbers 1 through 10. So if you could do me a favor now and press pause, I'd like you to go over these and make sure that everybody's on the same page. So get in your groups of 4 and go through 1 through 10, which was the homework last night. So I figure that'll take 3 or 4 minutes. Press pause. Okay, now that you're back, let's go through them. Number 1, which of these particles has the greatest mass? This is a table O lookup. You'll see the mass which is in the top left corner, and I'll bring table O up if you'd like. Top left corner. 4, alpha wins. It's the highest number on the whole table. Alpha, beta, neutron, and positron all on table O. The answer is choice 1. Number 2, which of these types of nuclear radiation has the greatest penetrating power? This is something we talked about back in the notes on page 2, I think. And that would be gamma, can get through the most. That's why you need lead or concrete to really stop a gamma ray. Alpha's dead layer skin, beta's a little bit more, maybe a piece of plastic. Neutrons also have some mass that they don't penetrate very far. Number 3, which type of radioactive emission has a positive charge and weak penetrating power? All right, clearly that would be the alpha particle. Now, an alpha particle is only a helium nucleus, which is why it is positively charged. Remember back to Rutherford's experiment, that was the positively charged particle that was being sent at the gold foil, was alpha particles, positively charged helium nuclei. All right, back to number 4. Which reaction represents natural nuclear decay? Well, number 1 and number 2 should be out right away because they don't have any other number thingies. All in nuclear reactions you will see will have number thingies. Now, we just talked about yesterday between natural and artificial. You can see that the uranium-235 is decaying to an alpha particle in thorium-231. The nitrogen-14 doesn't do anything until you bombard it with something like alpha particles. You can tell it's got 2 things on the left side, giving you some O17 and some protons out. So the answer there is choice 3. Natural nuclear decay is only 1 reactant. Given this nuclear reaction, what is this? This is, well, it follows along from number 4. This is natural transmutation. It is the release of a radioactive emission like a beta particle, and that's natural because it's cobalt-60, which happens to be a radioactive isotope. How do you know? Because it does something. You're not going to have to look at it and say, oh, it's a radioisotope. I mean, yes, you could look at table N and see a bunch of them that are radioisotopes, but that's not what this is asking about. 6, kind of a generic question. Alpha particles and beta particles differ in a few ways. Alpha particles are positively charged and they weigh 4. Beta particles are essentially electrons. They have negatively charged and have no mass. So they differ in both mass and charge. Number 7, that's choice 3. Number 7, which type of radiation has neither mass nor charge? Neutrons. We've been talking about that forever. Okay, neutrons have no charge. Oh, neither mass, no charge. Huh. Got totally blown up there. Sorry about that. It is number 1, gamma. No mass, no charge. Top number 0, bottom number 0. If you don't know, you can go to table O, and you'll see 0, 0 for the gamma. Okay. Number 8. Now some half-life questions. How many days are required for 200 grams of radon-222 to decay to 50 grams? All right, so here we go. 200, we have no half-lives, so count with me with your fingers, right? 1 half-life gets me to 100. 2 half-lives gets me to 50. So it's 2 half-lives. Once again, no half-lives for 200. 1 half-life gets me to 100. Second half-life gets me to 50. It's 2 half-lives. Now I have to look at table N and see what the half-life is of radon-222. Radon-222, 3.823 days. Let's multiply that by 2 half-lives, we said, so that's 7.64. There we are. Choice 3. Which radioisotope undergoes beta decay and has a half-life of less than 1 minute? All right, so this is clearly a table N question. You got to look up. All right, let's start with number 1, francium-220. Francium. Now, they are in alphabetical order, but not by element symbol. They're alphabetical order. Oh, I'm sorry. Yes, by alphabetical order by element symbol. So francium's over here. Francium-220, 27.4 seconds. But it's an alpha, so that's out. Potassium-42 is next. K42. 12.36 hours, that's out. N16, here we go. N16, 7.13 seconds. Beta, ding, 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 ding. Number 3 is the answer. Phosphorus-32 is beta, but it's 14 days or so. Based on reference table N, what fraction of a sample of gold-198 remains radioactive after 2.69 days? All right, let's see here. Gold-198's here, half-life's 2.69. Oh, well, half of it's left after that amount of time. That was an easy one. So sometimes they ask you by fractions. This is a little annoying on the format, but the answer is 2, 1/2. Okay, I'd like you to go back to your notes at this point. So we are working on number 3, I believe, on page 6. We're going to go through that. We'll go through a couple other things, and then I'll send you with some work to do, and then that will be the period. So these are questions that you've done already. How much of a 128 milligram sample of a radioactive substance remain after 4 half-lives? So you can make your little table. I'm probably going to be very bad at it right now because I'm not doing it handwritten. So number of half-lives. And do that. So here we go. At 0 half-lives, I've got 128. 1 half-life. I've got 64. Room here. For later. 2 half-lives. 32. You can do this other ways. I find this is the easiest way to do it. Why not just do it an easy way? 16. All right, one more. 4, 8, 8. And what's your unit? Milligrams, because that was the unit up here. So that's the way I would set up a table in order to do this question, just like that. And of course, you can go home and you can look at this table on the video and study a little more if you want to. What fraction? Oh, here's a fraction question. Of a strontium-90 sample remain up to 58.2 years. All right, for that we need to go to table N to find out, what we got for strontium-90. Let's see here. Strontium-90, 29.1. Okay, 29.1. So first thing we have to do is figure out how many half-lives that is. It's 29.1 year half-life. I've got 58.2 years. I got to do a division. One. Luckily, that comes out a whole number. It'll always come out a whole number, so it's 2 half-lives. This is a pretty easy one. For those of you who are trying to do it by fractions, it's not that tough, but in case you want to be good about it, let me show you how I would do this. Number of half-lives, and then fraction. Nothing wrong with doing it that way. A little line underneath. At 0 half-lives, my fraction is 1. I have everything. So it's just like 100%. It's still left. One half-life. Half. 2 half-lives. I have a quarter. 3 half-lives. I don't have to go that far because I only have 2 half-lives. Okay, right? That's what it said over here. So 1/4 is the answer. When you're done with your work. And this is all the work, actually. All right. What is the decay product from the nuclear decay of strontium-90? Write the equation. Well, if you did it again, great, good for you. But if you go back to page 4, you'll see that that's actually the one that you did already right here. Strontium-90, 9038. Strontium is beta plus yttrium-90. And so there you go. Don't have to worry about writing anything new there. So that number 5 goes back. Now, there is a formula. There used to be a formula, I should say. It used to be. No longer the case. This probably should have been erased from your notes. Used to be a formula on the back page of reference tables for half-life. It was awful. It worked, but it was awful, and I never let my students use it. So I guess they had a lot of teachers saying that, and so they scrapped it all together. So it's not on Trusty Table T. But I do want to talk about the uses for half-life. I'm going to get rid of some of these extra lines because I want this to match up with your notes. There we go. So by being able to detect, this is old news, really, this is earth science for you guys. By being able to detect the ratio of radioactive to non-radioactive elements in a rock, not Iraq, the country, in a rock, we can begin to determine how old things are based on half-life. For instance, if you find a fossil and it contains only a small fraction of the carbon-14 it originally contained, we can determine how many half-lives have passed since the bone or fossil was formed. This process is called radioactive dating. And on the next video, we'll do a little bit of work on radioactive dating, and then we'll wrap up this session. All right, see you in a second.